Hello, everyone. So this is the last video of the week, the one everyone's been waiting for, applications to business and economics. So some of the stuff we've talked about before. So the beginning is going to be a little bit like review, and then we're going to do a few new things with some of the functions we looked at before when talking about applications to business a couple of weeks ago. And then we'll, of course, apply our techniques of maximization, minimization of functions to these problems in business. Okay, so in business and economics, it's important to study, we study the following functions. So C at X is the cost function. So it's the cost of producing X objects or X units of the product. So this, of course, would be something you'd want to minimize in applications. R at X is the revenue generated by selling X units of the product. And P at X is the profit function, right? So this is profit from selling X units of the product. And the profit function is, of course, the revenue function minus the cost function. Okay, so cost functions we've talked a little bit about before. And recall the marginal cost is the following, is the derivative of the cost function. And the kind of reason for this, if you remember, is that if you wanted to estimate the cost of producing one more object, that's the same as the marginal cost of producing X objects plus the cost of producing X objects. So that's why it was called the marginal cost. The derivative was called the marginal cost because it can be used to estimate at the margin the cost of producing another item. Okay, so this is, so the marginal cost, it's just the derivative of the cost function. So we have, so I should say in some applications, it's important to minimize the marginal cost. I'm not going to go through an example like this. There's one on the homework. If you're stuck on it, we can talk about it during the live meeting. But it's a similar procedure to what we did in like the last several weeks in the last video and even before that. So in some, it's often, so it is often desirable to minimize the marginal cost function C prime at X and this is done by computing the derivative of the marginal cost function, which is the second derivative of the cost function, right? That's the derivative of the marginal cost, which is second derivative of the cost, and finding points where C prime double prime at X is 0 and then applying the first or second derivative test to these points, whichever one you like, just as we did in the last several videos. Okay, so I'll leave you, there's an example of this on the homework. I'll leave you to try this out. It's fairly straightforward. Once you get, what the terms are, remember marginal cost is derivative of cost. And to minimize the marginal cost, you take its derivative, which is the second derivative of the cost function, and then go through the procedure for that. Today, I want to do something new. I want to focus a bit more on the revenue functions and their properties and how to maximize, minimize, that kind of thing. So, and profits and so forth. So today we'll focus more on revenue. In this video, we will focus more on revenue functions. Okay, so we're going to be looking at the following situation. So suppose X units of a product are sold at, at a price of P dollars per unit. Okay, so like you're selling candy bars or something, each candy bar costs $2. I don't know what they cost these days, but so if you sell 100 candy bars and they each cost $2, you would expect that you would make the revenue from that sale would be $200. So in the case where you have a constant price per each unit that you're selling, then the revenue of selling X from selling X units is X times P, right? So this is the revenue from selling X units at price P. Okay, now the question is, what controls the price P? So that's where, this is all very simple stuff. Like I said, with the candy bar example, this is not shocking. But the question in the complicated models come up with the next step, which is what determines the price P? So question, what determines price P? Okay, so the price is controlled by something called the demand function or demand equation, which is P equals F at X, right? So the think of this is that price, this is a little bit tricky to think of, and it's not maybe the intuitive way to do it, but it's like relating this equation relates or determines, put it this way, determines the number of objects you can sell, or number of items you can sell at price P. Right? And it sort of determines the price for the number of items you sell, or the number of items you can sell at price P. So that's why it's called the demand equation. And so if we kind of put this fellow into here, we get a more like accurate revenue function. Like we get a nice model for the revenue function as a function of x. So substituting this expression for price into the equation, the revenue equals items sold times price, we get the revenue as a function of x, as a function of x items sold. So in other words, and so that function is just r at x is x times f at x. And that's what we'll work with. So this demand equation is very kind of mysterious thing a little bit to me. And it's almost set up, I feel like it's almost set up the wrong way in the sense that the roles of x and p should be reversed. But the book does it this way, so we'll stick with this for now. And they can have very complicated models for the demand function. But for us, we will consider linear demand functions. For us, fx, the demand function, sorry, for us, not use, will always be a linear function. So i.e., that is to say, fx will, p will be, this p equals fx, will be mx plus p. It'll be a line. Okay, so that'll make the problems doable. If you get into very complicated demand functions or demand equations, this gets very can get very complicated. So this might seem like a lot of mumbo jumbo. When I first read it, it did. But I think it becomes clear in an example what these objects mean. So the way I learned this is I kind of read the definitions like I just gave you, then I did the examples, and I came back and, I understood what the definitions were trying to say. So I'm trying to communicate to you that to you as best as I could, but I think you really need to see the example to get a feel for what these different things are really talking about. And the example is about baseball, which makes me happy because I'm hoping I can go to a baseball game this summer after everything that's been going on, and maybe even have a hot dog, although I'm not a huge fan of hot dogs. So hot dogs at the ballpark usually sell for $3.60 each. So hot dog. The hot dog stand sold on average, an average of 12,000 hot dogs on the night of a game. However, when the price was raised to $3.90 per hot dog, $3.90 per hot dog, the sales dropped off to 10,500 hot dogs per night. Okay, so the question is, I mean, what's better in some sense? When you want to maximize your profit, right? So there's these two competing interests. You can lower the price and sell more hot dogs, right? Or you can raise the price and then you'll sell less hot dogs, right? Because there'll be less demand for them at a higher price. And then the question is, well, what's the right balance? These two things are kind of fighting each other. And how do we maximize our revenue in this situation? So what's the right price to get the right level of demand to get maximum revenue? Okay, so that's what we're going to play with in this example eventually. Okay, so that's the second part of the question, but the first part is we have to understand a demand function, but that's where we're going. So part A, so part one of the question. So assuming a linear demand equation, find the price of the hot dog that will maximize the nightly hot dog revenue. Okay, so like I said, the first thing we got to do is find the demand equation. So solution, we first have to find the demand equation. Okay, so remember, we're assuming that the demand equation is a line. So this is f of x, and it's a line. So we need to find the slope and the intercept, b. M of this line and the y-intercept b. Okay, so we can find the slope, both of these things, because we already know 2 points on this demand equation, right? We know that if we sell, if the price is $3.60, we sell 12,000 hot dogs. And we know if the price is $3.90, we sell 10,500 hot dogs. So these are 2 points on this line. And using 2 points on the line, you can find the slope and the equation of the line. So we know 2 points on this line. Right? Namely, we know that if we sell, if 12,000 hot dogs, we can sell 12,000 hot dogs for a price of $3.60 and $3.60, and we can sell 10,500 hot dogs for a price of $3.90, i.e. this point, 10,500, 390 is on the demand line. P equals mx plus b, sorry. Okay, so let's do this. So the slope m is given by, so which one do I want to go first? I'll do this point first and this point second. So 360 minus 390 divided by 12,000 minus 10,500 hot dogs. Whew. If you work that all out, that's minus 0.3 over 1,500, and that equals minus 0.0002. Okay? So the slope, m, right, is 0.002. And so the price is mx plus b is minus 0.0002 times x plus b. And now to find b, we can just plug in either one of these points into this equation here. I mean, either one is good. So, sorry, either one of these is good to just plug into this guy here. So I'll use the first one again. So to find b, we plug in the point 12,003.60 into this equation. To get, okay, 360 equals minus 0.0002 times 12,000 plus b. And now you have to use a calculator. Okay, so you use calculator. It's already been done. And you get b is equal to 6. So our demand equation in this situation is price is minus 0.0002x plus 6. Okay, so now we can use this guy. We want to maximize revenue for the night. We got to figure out, right, what is the maximum level of price we can set and still sell enough hot dogs to maximize our revenue. Okay, so now we want to maximize revenue. So R at X, remember, is X hot dogs sold at price P. So now with this demand equation here, we can put this puppy in for P, like I was doing before, and you would get X times minus 0.002x plus 6. So Rx equals minus 0.0002x squared plus 6x. And we're going to maximize this function as we have in several videos now this week. Okay, now I am trying to be extra careful because let me just say, the most common mistake I make with these kind of things, with these application problems, is writing out all the zeros. That's why I keep saying 0, 0, 0 to myself, because otherwise I can easily miss a zero, and there's a lot of them, and then that will totally mess up the answer. Okay, so be careful with that, my experience. Okay, so let's see. So we take the derivative, we get minus 0.0004 x, right? So twice 0.0002 is 0.0004 x plus 6. Set this equal to 0 and solve. So if you do this, you get 0 equals minus 0.0004 x plus 6. So x equals 6 divided by 0.0004, and you need to use a calculator for this unless you're incredibly good with scientific notation. But you get 15,000. Use a calculator, and we can use a second derivative test. You compute the second derivative of this guy here. And it's easy. This is just a line. So the derivative of this is easy. 0.004, which is negative. So 15,000 hot dogs gives us our max revenue. So we got to find the price. To find the price that maximizes the price we should set, right? Set to sell these 15,000 hot dogs. We plug X equals 15,000 into the demand equation we found above. Which was here in star, right? See red star. Okay, so that was P of X was equal to minus 0.0002 X plus 6. And so if I plug in 15,000 hot dogs, I almost missed the 0 again. I told you I was going to do that. 1,000 hot dogs and 6, you get 3. Whew. So we should set the price at $3 to maximize the revenue. So much cheaper than the other prices that were mentioned in the beginning. Neither of those were right for maximum revenue. All right, so this is a complicated process, so I'll be more than happy to talk to you about this in the live meeting. I think $3 actually is kind of a lot for a hot dog, right? I mean, I don't know. It doesn't even think about the fixings. Like maybe those are free or something. But if you go to Costco or something like that, you can get a hot dog for like $1 or something like that. So $3, but is quite a bit. But at the ballpark, they're just jacking things up anyway. We won't go into that. But they rip you off at the ballpark. So it's always that way. Okay, now of course, the revenue isn't the complete picture, right? Because he's not just, you're not just gonna be able to make, all this funds from selling 15,000 hot dogs. You have some costs, right? There's a cost keeping the concession stand open. People work there, they have to be paid. And, you have to buy the hot dogs and maybe the condiments, but we're not even getting into that. So, there's going to be some costs involved in running the stand. And the profits are the revenue minus the cost. So we've got to kind of, if you want to have a realistic picture of what kind of a night we're having running this concession stand, we need to play with this a bit more. We need to think about the costs. So let's consider the costs of running this that we'd incur tonight too. Okay, so suppose the hot dog stand has a fixed cost of $2,000 per night. Now, what does that mean? So that means that no matter how many hot dogs you sell, right, this just costs $2,000 to keep the hot dog stand open. So to have the people work there, paying people work there, keep the lights on, the power to run the hot dog stand. Okay, so that's no matter how many hot dogs you sell, that's fixed cost. But there's also a variable cost. The variable cost has to do with how many hot dogs you sell, right? Because you have to buy these hot dogs, right? You don't come from the sky. You have to buy them. You go to Costco or whatever and buy all these hot dogs. So there's a cost involved in how many hot dogs you're selling because that determines how many hot dogs you have to buy, right? So there's also a variable cost of 50 cents, well, so $0.5 per hot dog. In other words, so i.e., each hot dog costs you 50 cents to acquire. Okay? Now we want to find the price of the hot dog. That will maximize our profit under this situation. Okay. Okay, so we know we want to maximize. So here's a solution. So we seek to maximize profits which is the profit function P at X is the revenue function minus the cost function. Now we already found the revenue function earlier. So we found this in previous problem. So what did we find? What was it? I gotta go up and grab it. There it is. But we need to construct the cost function from the information given in this part of the problem. Above. Okay, so what are we told? So, right, it's $2,000 just to keep the lights on in the hot dog stand, and it's 50 cents per hot dog you sell. It costs you 50 cents to acquire a hot dog. So the cost is this fixed cost plus the variable cost times the number of hot dogs you need to acquire, right, in order to sell them. Okay, so that's the cost function. So it's, if you want to think about it, it's fixed cost plus variable cost times X, right, times the number of things you're selling. Because that means that's how many you have to buy. We're not worrying about things being left over. It's just, you're making the assumption you're selling them all. Okay, you're not worrying about waste. That's another complication that we won't get into. Okay, so then the revenue function, right? Sorry, the profit function is revenue minus cost. We have the pieces now. So then P at X is minus 0.002 X squared plus 6X minus the cost, minus 2,000 plus 0.5X. And you got to do some math here, simplification. So P at X then comes out to be 0.002X squared minus, plus 5.5X minus 2,000. Okay, and so this is straightforward. I mean, it just take 6x and subtract half x and make sure you distribute the negative sign here. Now, this is the thing we want to maximize, right? So now we maximize this using calculus. So you get p prime at x, take the derivative, again is minus 0.0004x plus 5.5. Set p prime at x equal to 0 and solve. And you should use a calculator to do this. When you do this, I won't write it all out. You get x equals 13,750 hot dogs. And you can use the second derivative test again if you want. It's the same thing as before to see that this is the maximum. P double prime at x is minus 0.0004, which is negative. So this is a maximum. And now we just need to find the price. So we go back to the demand equation star, which is long gone. Way up here. Copy it. Oops, sorry. So to find the price, we need to set, we plug 13,750 into the demand equation star, which I copied from above. And you get P at 13,750 is minus 0.0002 times 13,750 plus 6, and that works out to be $3.25. So to maximize our actual profits with these cost parameters, so the fixed cost of opening the stand, $2,000, and have to pay 50 cents to get a hot dog, for us to get the owner to acquire the hot dog, each hot dog, we should set a price of $3.25 to maximize our profits. So under these cost parameters, we should set a price of $3.25 to maximize our profits. All right, so I think this is kind of fun. I mean, it's interesting. You can kind of see how in real life now, these are complicated questions, right? Like you set a price, a certain price, people only buy a certain number of hot dogs. And if the price goes up, they're going to buy less. If the price goes down, they'll buy more. But then what's the right level? What's the right balance to get the most revenue? And then you have how much you're paying for the hot dogs. So like, you might need to sell more hot dogs and get less revenue to offset the cost, right? So it's a complicated game. These different things are fighting each other, and the calculus tells you how to sort all this out. So I find that really interesting, and I hope you enjoy it too. So these are tricky. There's a couple of these on the homework. I think one deals with hamburgers, and maybe it's not a baseball game, or it's like a, football game or something like that. But it's a similar idea. So go through this example carefully. You should be able to do all the homework problems. I didn't explain how to minimize, or I didn't do an example, sorry, of how you minimize the marginal cost, but I explained that. If you're stuck on that, I'll be happy to talk to you about it in the live meeting. So I will see you guys then.